Okay, it is, so I'm Eric Clavens. I'm a professor in the department and the current chair, and it's my pleasure to introduce Assistant Professor Akshay Gadre, who received his PhD some months ago this year from Carnegie Mellon University, and he started as an assistant professor in our department at the beginning of this fall quarter. We're very excited to have him here. He studies low power wireless systems, as he'll describe today, with applications to Internet of Things and sensing in space and on Earth. He's actively recruiting in his lab. I think he's working with undergrads, master's students, PhD students, the whole works. And yeah, he's super fun. Oh, and he's a pretty good chess player. So if you like chess, you should come to our graduate student socials and challenge him to a match. And even better would be to encourage him, because he said that he would like to actually run a chess tournament in our department. And so if you come and express your enthusiasm for that possible event, then that may actually happen. And you can, and I'll be in the tournament, and you can beat me because I'm really bad. And you could say you beat a whole bunch of professors. So anyway, with that, I'm going to turn it over to Akshay. Thank you so much for giving our colloquium today, and also thank you for joining our department. We're very excited to have you.
Thanks, Eric, for the great introduction, and hi, everyone. Thanks to all of you for watching online as well as are here in person on a snowy night. So it's good to be here at UWECE, and today I'll be talking about rethinking low-power Internet of Things on Earth. But before I dive into what I do as a researcher, I want to briefly discuss about what I do broadly as an expert. And I basically build wireless, mobile, and cyber-physical systems. For example, you would see me deploying sensors around a city, carrying antennas in a bag, and taking various measurements by walking across a city and understanding the behavior of all of these devices and sensors deployed in a city. Another set of things that you would see me doing is actually flying drones indoors and trying to understand what happens when you take the mobility of these quadcopters and small drones indoors, and if you want to deliver packages indoors using these drones. Another set of projects I looked at creating ultra-fast millimeter wave links, where we actually built a test bed and showed the fastest bidirectional full duplex link at the time that we did the project. I've also worked with industry on building supply chain sensing solutions, where we actually built a solution for testing product integrity inside a package. For example, many a times you ship like precious things like glass artifacts and they reach to you broken. We could build a system that could detect those breakages during the supply chain itself. And finally, more recently, I've been exploring communication with CubeSats, and this actually is might become a historical picture in like a few years, because this is the first ever packet received from an off-the-shelf LoRa chip from an actual CubeSat in sky. And with all that introduction, let me go back to the start of my journey as a researcher and explain how I tried to understand these problems and solve them. So when I was starting my PhD in 2017 as a new person in wireless, Internet of Things was a really, really hot subject, where people were building systems like mobiles, laptops, and computers, but also systems that connect with these systems. For example, a projector in this room, or a printer, or a microphone. Another set of products that were becoming really hot in the market were smart bulbs, or like smart doorbells, Amazon Ring, for example, or like smart switches, where you can just say, hey, Alexa, turn on my lamp, and it would turn on the lamp. And as we were thinking of creating new solutions to augment the world around us, the next frontier really was, hey, we have augmented all these measurements inside our house. Let's try to augment the data which is outside our house at a city scale. And really, that's where the new era of IoT really started. When we looked at new problems outdoors, we started creating sensors for measuring road vibrations to estimate whether the road is good or not. And we can tell the city services that, okay, the road is bad and you need to repave it. Or we would have electricity meters and water meters which would be able to bill us automatically. Today, when you use Seattle Light Services, you can see your daily usage continuously using similar kind of sensors. Also, around UW, you would have seen many of these smart trash cans. The trash cans tell the city services that, hey, it's time to pick up the garbage. And similarly, there are also other kinds of sensors we developed, like flood sensor and air quality sensor. And these were not restricted to only urban towns, but even rural areas. For example, you would actually build forest management sensors to understand when a forest fire or some calamity is going to happen in a forest and to manage the forest environment. Or even smart farming solutions where you can use these sensors to decide when to irrigate a farm. And as we started putting these sensors outside, the biggest restriction we really felt was, hey, now we either have to provide power to these sensors or to provide a base station service close to the sensors. Like, for example, we know how bad the Wi-Fi service gets once it goes outside the house. So you cannot service these sensors with that wireless service. And this led to 3 key modalities that were needed to develop to augment the city-scale Internet of Things. You needed a wireless technology that could enable a long range of communication so that you can deploy a base station at house, and across your farmlands you can have these sensors. Another big requirement was for it to be low power. If you deploy a sensor, you don't want to go there every day to change the batteries. It's too huge of a management task and would be almost difficult to make them scale at any point. And finally, we need a solution that is easy to scale, which means you don't need to deploy a lot of infrastructure. Just deploy one base station somewhere in the city, and you can augment the whole city-scale Internet of Things. And it was with this vision that a new class of wireless technologies was being developed called low-power wide-area networks. This is basically a wireless technology to connect long-range IoT devices in a city or in a forest environment. These technologies claim to provide a range of 10 kilometers, could last up to 10 years on a AA battery cell, and could provide a data rate of few kbps. And this is not some niche technology that's going to occur in only specific use cases. In fact, over 1 in 4 wireless industrial IoT connections will be using LPWANs by 2025, and the number is set to go up to several billions. And when you actually have these devices deployed outdoors, the obvious thing is now we have the data, let's try to do some inference tasks on these IoT devices. For example, you might have deployed temperature sensors or rainfall sensors or even snow sensors to estimate the weather in that area. And we want to use the data to estimate what the weather is looking like. Or you might use the soil moisture sensors to understand when you want to irrigate a farm. Or you can use pollution sensors deployed in a city to help breathing impaired people to avoid those high pollution areas, especially in cases of forest fires, as we have seen. Now, if you want to do typical inference on these IoT devices, the pipeline looks something like this. You have a few IoT sensors, and then you will collect the data using the wireless technology such as LPWAN, and then perform machine learning or statistical inference using the data that we received. For example, on a farm, you would deploy, let's say, 4 soil moisture sensors, and you will continuously measure the soil moisture data. Whenever it goes below a threshold, you will just start the irrigation system, and the soil moisture will increase. And you can use this data to make a decision on whether you should irrigate. However, this typical inference pipeline makes 2 key assumptions. First, the wireless communication can enable the retrieval of good amount of data from these IoT sensors, and the inference algorithm gets enough data to make that useful inference, right? And unfortunately, this inference pipeline breaks down for LPWANs. Instead of looking something like this, the inference pipeline looks something like this, where the wireless communication medium can only allow a few kilobits per second data, so you can only retrieve a small amount of data from all of these sensors. And because you have so little data, all these data-intensive algorithms lead to bad inference. Of course, there have been ways, like people who have built solutions, including myself, to improve both of these components individually. For example, on the wireless communication side, I have done several projects on coherent combining, smarter MAC layers, and automated configuration to get as much amount of data as possible from the IoT sensors to the base station. On the other side, people in machine learning and data science expertise have developed new solutions which use little amount of data to build useful inference solutions using sparse recovery, sketching, deep learning, or even reinforcement learning. However, this individualized approach to target both of these problems is not enough to solve this problem because you will never be able to break the data bottleneck. Instead, my approach takes a holistic approach of co-designing the wireless communication layer and the inference algorithm together. And using this principle, today I'll be talking about two projects which I did during my doctoral studies. One is a Quail, which deals with low latency IoT inference at scale. And the other is Vista, which enables low latency imaging from CubeSats. So without further ado, let's dive deep into the first project, which is Quail. To understand the problem that the Quail is trying to solve, let's look at a deployment example in a forest. Let's say there is a forest in a rural area, and here each tree represents a large area of the forest. Because LPWANs enable long range of communication, thousands of these clients will be connecting to the single base station. Now, let's say one day there is an anomalous behavior in a forest, like let's say a forest fire. Now, instead of caring about data from all of these individual sensors, whether it's fine or not, we start asking questions such as, hey, where is the fire originating? Where is it spreading? And which areas should be evacuated? These kind of unexpected events, such as forest fire, require quick information from aggregates across clients. Now, unfortunately, there's a huge dichotomy between the kind of use case LPWANs were built for and the kind of data that these special queries require. LPWANs were built to occasionally wake up, send a little bit of information, and go to sleep. Whereas special queries require a quick response from all of the clients, giving an aggregate information understanding to the base station. Now, of course, there are solutions to retrieve data from a lot of IoT sensors. For example, the easiest solution is polling. Let's go and ask every client what your data is and try to understand whether the forest fire is starting. However, it is too latency intensive. It could take up to 3.5 hours when you go up to 10,000 clients. Another approach is sparse sampling, where you query a few of those clients and then interpolate the behavior for the sensors that you did not measure. However, in the case of a forest fire scenario, it requires still too high of a latency for any relevant accuracy because only a small area of the forest is burning and you have to luck out on selecting one of those clients. And finally, there have been parallel processing solutions which decode collided packets together, which is low latency and high accuracy but does not scale to more than 6 to 7 clients. Now, there has been this prior work on LoRa to retrieve this data has these approaches. And inference algorithms, which are typically built for forest fire detection, collect data from all of these sensors. And in the middle lies the problem of forest fire detection. Now, if you just use off-the-shelf LoRa approaches to retrieve data and then perform inference, it could take up to several hours, which would be too late to actually do any good work because of early detection. However, the goal we really need to achieve is to perform this detection within a few seconds. And so we asked a simple question. Can we quickly retrieve an estimate of the aggregate information of LPWAN radios in a forest? And we say yes. We present Quail, a quick aggregate query solution for LPWANs. It's a system that can perform aggregate queries on thousands of LPWAN nodes within the duration of a single LPWAN packet. It's compatible with both the popular LPWAN technologies, LoRa and NB-IoT, for statistical, spatial, and inference queries. And it achieves 4x faster information retrieval with 2x lower error over sparse sampling solutions for network scale inference, specifically for the forest fire example. And how does our solution work? Go back to the basics and take the unified approach of co-designing the wireless physical layer and inference algorithms. Now, you want to retrieve information from all of these clients, and you want to achieve it within a few seconds. So we asked, hey, why even a few seconds? Let's try the fastest way possible. Let's make all of them transmit their information at the same time. Now, anybody who knows wireless communication would know that if all of them are shouting at the same time, you won't be able to understand what each client is saying. In simplified words, let's say everybody in this room was shouting a random word, I wouldn't be able to hear individual words out of all of your mouths. However, One thing that I would be able to tell is how many people are there based on the loudness of the voice. And we use the similar principle for understanding how many of the clients are actually alive and burnt off to build Quayle's primitive. And the Quayle's approach builds on the scientific principles of how wireless powers add up. Let's say we have a client deployed in a city away from a base station, and then another client deployed at roughly the same distance, and they are both sending the same amount of energy to the base station. Now, if they are perfectly in phase, their amplitude will double, and hence you will receive 4x the power at the base station. In the worst case scenario, they would completely cancel each other out, and you will receive no power at all at the base station. However, if you take the average case scenario, you will receive the twice the amount of power at the base station. And to understand this beyond just 2 clients in a mock scenario, we actually went out and did a large-scale study in the city of Pittsburgh by deploying 20 clients in actually, as well as performing trace-driven simulation for up to 10,000 client collisions. And our results show that wireless powers adding up linearly does scale to 10,000 clients. In fact, as the number of clients goes larger and larger, this becomes more and more the case because of law of large numbers acting up, which means all the noisy behavior and adding up and destructive behavior cancels each other out, and you get the average case behavior. Now that we know that the wireless powers add up linearly, Quayle's approach is to encode the information in the wireless powers being transmitted by these clients. Let's say these 2 clients were calculating temperature, and they want to communicate the sum of their temperature to the base station. You would encode their energy such that the received power at the base station would be 20 milliwatt and 30 milliwatt, which is proportional to the measurement at the sensors. Note that there's a lot of wireless system building that you need to do to achieve this, but upon doing this, you will receive these powers. Once you receive these powers at the base station, these powers will basically add up linearly, and you can use that to make an estimate of what's the mean temperature across 2 sensors. Similarly, you can send something proportional to a small function of the sensed information. For example, you can send power which is proportional to the square of the sensed information, which in this case would be 4 milliwatt and 9 milliwatt, and that would allow us to find the variance. And similarly, you can also pre-multiply with a simple constant like half to find the mean directly. Now, all of these primitives, what they're trying to tell us is that we can get simple weighted linear combinations of simple function of sensors data at the base station in a single time slot. Now that we have built a primitive that can allow us to encode information from all of these thousands of sensors into a single time slot in the form of a weighted linear combination of simple functions of the sensed data, what can we actually achieve with just this simple form of information? So one kind of queries, as we have already seen, is statistical queries. For example, you can compute the mean, median, mode of data across a large number of sensors, even the variance, sum of the sensors, and count of the sensors who are participating in the query. Then we can even process inference queries because many of the data-driven solutions require a linear weighted combination at the first layer, for example, like a neural network, which can be passed on to the neural engine for further processing. And the final set of queries we address in this solution is spatial queries. Let's say we have a spatial distribution which these sensors are measuring, let's say like the forest fire scenario that we looked at. If you look at it from the sky, what these sensors are measuring are pixel values of an image from the sky. And these pixel values can be thought of like measuring an image. And there have been a lot of work on developing compression algorithms for images. For example, like JPEG or PNG or other transforms that compress images into a small representation. And a key component of many of these compression algorithms are sparse transforms. And many of these transforms are inherently linear so that you can do this compression quickly on the go. And since we now have a linear compression algorithm, we can just apply that linear compression using the Quayle's primitive to by leveraging these linear transforms to communicate the client's contributions to the above compression algorithm. For example, let's say this is the actual distribution that these clients are sensing, and we have a few clients deployed in the environment. And let's say we pick a linear transform such as DCT or DWT for the case of an example. What each of these clients will compute is its own contribution to each of the DCT or DWT components. And since we know most of the information is aggregated in the top left corner of the DCT matrix, only the top few components are sent at different time slots to the base station. At the base station, you will only receive the top few components. Because of the additive nature of wireless powers adding up, these components will actually represent the actual DCT components of the actual distribution measured by some sparse sensors. And these top few components can be used to reconstruct the underlying behavior that we are trying to detect. For example, this measurement actually corresponds to this behavior that we can get. Although it's like kind of vague, we can still identify that there are areas where the sensors have been burnt out, which can be useful in making a quick decision. And this is the Quail's reconstructed distribution. And thus, this is how we would build a system for a quick aggregate queries on a large number of sensors deployed in the environment. Let's say, now we have seen the example of a forest fire, but are there other applications where this would be useful? Well, yes. For example, you can use statistical queries to identify how many of the IoT sensors deployed in a city have upgraded to the next level of the firmware. Or you can use inference algorithms to build a smart irrigation system on a farm, or build spatial solutions to identify the distribution of pollution in a city to help breathing impaired people avoid those areas. Of course, I made it sound all very direct, but there were several other challenges that we needed to solve, which are described in our manuscript, like enabling collisions in technologies which avoid collisions inherently, compensating for the wireless channel, dealing with frequency and timing offsets, and reliability in the presence of noise, where we built a new solution. More details are in my thesis or in the manuscript. We implement the system using actual software-defined radio base stations and off-the-shelf LoRa radios. We operate the radios in LoRaWAN and FSK mode to simulate the behavior of LoRa node or NB-IoT client, and much of the processing was done in the cloud. And we actually went out in the wild and collected 150,000 GPS tag channel measurements across the city of Pittsburgh. So there are hills around, there are tall buildings around, and all the real-world scenarios that you would typically encounter. And our main evaluation was to understand the forest fire case study. Let's say there is a forest fire burning. Now, of course, we can't go to a forest and burn it down for our project, so we did trace-driven simulation. And you want to get a rough estimate of how the fire is spreading and how quickly we can retrieve information from 10,000 clients. We compare Quail with sparse sampling approach with interpolation and an ideal version of Quail where all the wireless impairments don't affect the quality of solution. At first glance, you would see that to receive 90% of the information, all of the solutions work pretty well. And this is not in fact surprising, because just saying that everything is green is good enough to get 90% of the information. Only a small area in the forest is burning, and to detect that is the really useful things. And that's where Quail simply outperforms the sparse sampling solution. We do have some non-idealities because of the nature of the wireless channel, but it's not too strong to make our solution unusable. And thus, we achieve 4x faster retrieval for Quail over sparse sampling solution. Remember that this is the worst case scenario for Quail, because sparse sampling solution gets 90% of the information very quickly. So in a real world scenario, Quail would perform even better than 4x faster. And with that, I would end the discussion of Quail, and I'll be happy to take a breather and see if there are any questions. Yes?
I think I got confused when you started talking about the spatial. So these 10,000 sensors, are there multiple at each of your sites of the forest fire, or each of the sites of your spatial map?
Yeah, so that's a good question. So the question was like, hey, what do these sensors measure when they are deployed in the forest, and where are they actually being deployed? So of course, we didn't deploy 10,000 sensors because that's difficult, but we assume that each of these sensors is just a temperature measurement device. And in the forest fire scenario, based on our talks with forest fire experts, either they'll be burned down, or they'll be sending a faulty data, or they'll be sending like the right data. And those are the three categories we assume that the client is transmitting, and we use that to distinguish. And we assume that they are being deployed in a grid. If they are not being deployed in a grid, there will be slightly more errors, but not significantly more errors.
Can you go back to the slide where you did the spatial
Yeah.
picture? This
Yeah.
So are there many sensors at each of those sensor places where you have a picture to sensor?
Yeah, so no, so we assume that there's only one sensor in each location, and together they know their geostationary location on the grid, so they are able to build this kind of a matrix because they know their contribution to each of the spatial locations.
And you're measuring the average of all of them, but with different timings? I was just trying to figure out how this related to the quail where you were measuring the average.
So we have like lot of measurements which each sensor wants to send, and instead of sending all of these sensor measurements together, they just send like each of the pixel in a time slot. Now we can't send all the pixels because it's like just too much of a work. So instead we just send the top few components of the pixel, and we can time slot that out at the query phase. Yeah. Cool. So for the constraints of time, I'll move on to the next project, and I'll keep time at the end for questions as well. So let's move on to the next project where we build a system for low latency imaging from CubeSats. And before we try to build a system for CubeSats, let me try to explain what are CubeSats. So CubeSats are basically small sensors which are 10 centimeter by 10 centimeter by 10 centimeter cube, and they're being built as small satellites which you can send to space. The reason they are being built is because it's cheaper to deploy. They are extremely low weight, and our modern technology can actually miniaturize many of the research things we are trying to try out in space into these small sensors. And most of them are easier to deploy because of low weight and the low orbit that they occur in. In fact, when I was at Carnegie Mellon, our collaborator participated in a VR3X mission where we sent these 3 CubeSats up there to identify ranging and localization. And these are not just devices that are hovering around Earth. In fact, the Marco CubeSats have been deployed on Mars to image the surface of Mars as well. So this is an actual live video from a CubeSat being deployed on Mars, which is trying to image and just test out the possibility of deploying CubeSats on Mars. And herein lies the true frontier of low power IoT, which is in space. We are talking about these small cubic sensors which are orbiting around over our heads, and we are going to try and communicate with these sensors. Most of these sensors are roughly at the altitude of 500 kilometers, and there could be multiple of these sensors at the same time above the sky of a big city like Seattle or Pittsburgh. And to really have all of these sensors overhead, the obvious question is, how do we communicate the information collected at the CubeSats down to Earth? Now, to understand this, we analyzed the trajectory of our CubeSat that we launched in 2021, that our collaborators launched in 2021. And as you can see, the CubeSat goes around the Earth pretty quickly. However, on the left side, if you notice, if you look at the city of Pittsburgh, the CubeSat is overhead only for a small amount of time in a day, which is just 15 minutes. And whenever it is there, it is only able to send a few amounts of packet down to Earth. So we basically need connectivity all around the Earth to keep collecting data from the CubeSat. Now, one approach to collect data from these CubeSats is to use existing satellite ground station network. Let's say we are super rich and we can employ all the existing satellite ground stations that exist on Earth, which are big and extremely costly to deploy. And to understand this, we analyzed the orbit of our satellite over the 2 to 3 days, and we found that there are still many locations in developing countries and in locations where we don't have land to deploy these base stations, where we are not able to receive the data quickly enough. In fact, in many locations, the latency could be as large as 60 to 80 minutes, which is like roughly 1/8 of the orbit of a satellite base station. Now, obviously, nobody is going to be able to employ all of the ground station infrastructure and be able to communicate and still have this bad of a quality of information reception, right? So we asked an obvious question. Why do we use these expensive infrastructure when there is a already existing infrastructure being deployed on Earth by all of us companies at a cheap cost? Specifically, we ask the question, can we somehow enable these CubeSats hovering in space to connect with the existing low power IoT infrastructure so that we can enable widespread connectivity around Earth? So we picked a technology which was our favorite, which is LoRa at 915 megahertz. And we found out that if we use LoRa at 915 megahertz with its extensive ground station network, we can enable a lower latency compared to all of these expensive base stations put together. And this is obviously the best case scenario for satellite and worst case scenario for LoRa. You'll never be able to get all of the satellite ground station resources. And so these 915 megahertz LoRa ground stations are a good alternative for providing low latency connectivity to these cube satellites. And this is not the only benefit. There are several other benefits. Other than the existing ground infrastructure, LoRa technology is already resilient to terrestrial interference in the same band because it's built to operate in that band. And it's also scalable and spectrum efficient, which means tomorrow if you have thousands of CubeSats in the air, you can still use a single base station to communicate with all of them. So what's the catch? Well, first, when people were developing LoRa as a technology, the fastest speed they thought would be a car moving at 60 meters per second. Unfortunately, satellite in the sky is moving at 7,000 meters per second, which means it faces a massively larger Doppler compared to a car. And finally, let's say we collect some image data at the satellite, and we want to send it back to the ground. Unfortunately, you can only send 256 byte packets, which means the kind of information you can send is something pixelated like this, which is not very useful. And this basically is due to the low bandwidth constraint of the LoRa technology. So LoRa is not really designed for space applications. To understand the effect of Doppler, the Doppler curve for our CubeSat, which we launched operating at 500 kilometers, looks something like this. And the detection limits of the off-the-shelf LoRa base station chips is significantly smaller. And what this means is instead of receiving many of the packets in a single pass overhead, we were only able to receive 2 to 4 packets in every pass. Another problem is the effect of limited throughput. So let's say we are capturing an image of, let's say, industry, and we want to do some kind of compression so that we are able to squeeze the information inside a 256 byte packet. We would need to do some kind of compression where all of the possibilities is like really bad. Now, there have been prior LoRa CubeSats. However, these LoRa CubeSats circumvent the problem of Doppler and bandwidth constraint by operating at a lower frequency. By operating at a lower frequency, the Doppler behavior is within the constraints of packet detection limits of off-the-shelf base stations, and hence, you are able to receive packets from just off-the-shelf base stations. However, if we use low-frequency LoRa clients on the satellites, we'll have to deploy custom hardware again on the ground, negating all the benefits we were receiving of using existing hardware, which means the latency of using 450 megahertz base stations is even worse than satellite ground stations. So again, whenever we see these kind of curve, we ask a simple question. Can we perform low latency inference on LoRa-enabled CubeSat images by leveraging existing ground infrastructure? We say yes. We present Vista, a low latency imaging and inference solution for LoRa-enabled CubeSats. And what we did, we overcame the throughput and Doppler constraints of the LoRa technology. We designed channel-aware data task-driven encodings to retrieve these images. And we achieved a significant improvement in image retrieval SNR and improvement in classification tasks over the images. And the latency improvement is already shown previously, so you know already. And how do we do this? We go back to the basics. We take the unified approach of co-designing the wireless physical layer and inference algorithms. In the case of the LoRa CubeSat, what we do is we take the image and perform a Doppler resilient encoding on the image. And at the ground station, we build an inference decoder that is able to detect the signals which are Doppler offsetted from this cube satellite. Our approach makes a key observation. Our satellite is not the first one to operate in this orbit, right? There have been several other satellites such as Sentinel-2, Landsat, NOAA, built through extensive research by our amazing scientists. And we have data available from these other imaging satellites. So we have already a large set of images taken from the same altitude. Another thing which we know is the tasks that are going to be performed on this data can be known a priori. For example, we might want to do land use classification, whether this image is of a factory or an industry, or whether how is the weather looking like in a city. And then we can use the CubeSats that we launched to understand a channel model from the satellite to the ground stations built upon existing measurements of our CubeSats as well as existing theoretical LEO models. So if we were to start solving this problem, the first solution is let's go to deep learning and machine learning and build a data task-driven encoding where we compress the image into within certain constraints and then use that encoding to perform inference tasks and image reconstruction. For example, you can use this encoding to identify that this is an industrial system and this is what it looks like roughly. Now, this would be great and this would be an ML solution, except that there's this wireless channel in between that is corrupting the data. Specifically, there are two sources of information loss that we face in the air. First is discretization, because you cannot send analog data, you need to encode it in bits on the LoRa technology. And then there is noise and Doppler, which affects the bits in a very surprising way. And to really build a solution that is aware of these problems, we build channel-aware data task-driven encodings. And we do this by training our system in two phases. The first phase tries to make our system resilient to noise and Doppler. So many of you who are wireless experts might know that noise causes roughly uniform effect across bits. However, there's another problem which causes errors in the case of LoRa CubeSats, which is intra-packet Doppler, which causes a non-uniform behavior of error across bits. To understand why, let's look at an example. Let's say this is the LoRa technology. It's encoding some information over the air. Because the satellite is moving so fast, across a single packet, the Doppler accumulates. And because the Doppler accumulates, while noise causes you to pick a random bin, which is uniform behavior of errors, the Doppler behavior just causes a small shift in the frequency bin, which means that the most significant bits are more resilient to the Doppler errors compared to the least significant bits. We use our measurements from our Cube satellite as well as existing channel models to understand this distribution of symbol errors and roughly how many frequency bin offsets happen because of those errors. And using that, we built an intelligent bit flip black box that you can insert during the training phase to train our system to be resilient to these non-uniformities. Another problem that we intend to solve is the problem of discretization. Now, there have been approaches which have done this before, and we take the simplest approach to solve this problem, in which instead of retraining the whole network where we have a bit flip black box, which is impossible in this case because discretization is not a continuous process where the gradient can flow over. We freeze the encoding layer because we know it efficiently encodes the information and just train the decoder to be resilient to the discretization errors. Apart from building a solution for channel-aware encoding, we also build solutions for trajectory-aware Doppler estimation at the base station. I've left out the details of that for the brevity of the talk, but broadly what we do is we use wideband preambles for detecting high Doppler packets. We built a high-resolution Doppler estimation solution, and we leverage the trajectory estimation to fine-tune the estimates of the Doppler so that we know exactly where the packet is and are able to decode it. We implement Vista and evaluate it using off-the-shelf base stations on the ground, such as USRP SDR, as well as SX1262 LPWAN radios. The obvious question is, how do we evaluate sensors in space? And we were lucky to have amazing collaborators who are actually deploying satellites at roughly the same time. So these were the 3 CubeSats that our collaborators were deploying in space and they were actually operating using the LoRaWAN technology, sending packets to the ground. And once these CubeSats were up in the air, we were able to detect the packets from these LoRa CubeSats and able to build our channel model. As you can see, our channel model mimics the behavior of real Doppler behavior very accurately. After modeling this behavior, we used existing data sets of Sentinel-2 image patches to understand the behavior of our system. And the two goals of our system were to perform image reconstruction and land use classification. The pipeline looks something as follows, where we take an image, we encode it into channel-aware encodings, which is then discretized and sent over the air. The noise and Doppler affects the signals, which are then used to perform image reconstruction and land use classification. So you remember when Doppler was causing all of these packets to be not detected? Well, using our system, we were able to detect all packets in a particular trajectory. And obviously, we are going to lose information because we are doing compression, but we try to preserve most information useful for our inference task using Vista. Oh, yeah.
Yeah, just a question about the operation. So the satellite velocity to the land-based receiver should be well known, right? So I thought it would be easy to just calibrate the Doppler shift, right?
Well, that would be definitely easy, but in fact, there is a key takeaway in our paper where we say that it is very difficult to get the NORAD ID, which gives us the trajectory of the satellite actually. And in fact, you need to estimate the trajectory of the satellite in the first few months because the NORAD ID is received after 3 months. And the lifespan of a satellite is just 1 year. So if you don't operate for the first 3 months, it's basically you're wasting very important and costly infrastructure. So we have solutions there to actually estimate the trajectory and identify the Doppler behavior and hence detect the packets. So that I left it out for the brevity of the talk, but I'm happy to discuss it offline.
That's a unique problem to lower orbital satellites, right?
Yeah, in fact, trajectory estimation is a big problem for these small CubeSats because they come in the lowest order of finding the NORAD IDs. There's like more important, bigger satellites that get the priority above these smaller satellites. So broadly, we achieve 4.56 dB image PSNR improvement, and we achieve a higher classification accuracy. You can go over the results more deeply, but the thing which I want to highlight is using just the blotchy image, we are able to distinguish most of the things except highway and industrial scenarios. Because in a blotched image, you would say both of them look like concrete things. But what Vista achieves is it keeps the behavior of a highway looking like a river and industry looking like a block and preserves that information for achieving a faster accuracy. And apart from these two projects which I discussed today, I have contributed a lot of other projects and contributions to low power Internet of Things by building IoT analytics and inference systems, improving the infrastructure capabilities, and improving CubeSat IoT connectivity. Apart from low power IoT, I've also built millimeter wave full duplex radios and solutions for acoustic packet sensing. Yeah, I'll wrap up in a few minutes because of time. Before I go on, I would like to thank all the funding agencies, all the people who worked on these projects. Now that I have done all of this exploration in low power IoT, my future research is going to explore new application domains and technologies. Specifically, 3 areas that I'll be looking to explore in my lab is going to be satellite IoT, on asking questions about the modern deployment of satellites in terms of constellations. In agriculture and forest IoT, where we try to understand the health and behavior of the plant using new wireless technologies and augmenting the rich wireless signals in industrial scenarios to build industrial IoT systems. As we move towards a data-driven world, we as wireless researchers will have the responsibility to augment new data sources, co-design wireless for data-driven tasks, and develop wireless-aware data-driven applications to enable a data-driven world tomorrow. And we as ECE researchers have the unique opportunity to bring our data science expertise from computer side and electrical engineering domain knowledge from the EE side to build this better future together. And of course, if you want to join me in this process, I'm looking for students to join my new lab. So don't forget to apply it for the PhD program. And with that, I would like to thank all the online audience and the live audience for attending the talk. And I'm happy to take questions.
Great. So are there questions for Akshay?
Have you done any work with the Husky satellite team?
Not yet. I've just been here 2 months, but I've talked with them during the interview phase as well. We are planning on doing some collaboration, but like I've been kind of settling in at the department yet. But yeah, I'll definitely be interacting with them. Yeah.
And for YouTube, the question was, has he done any work with the Husky
CubeSat
satellite CubeSat team?
Yeah.
Other questions?
So to kind of simplify, with Quail, you're kind of measuring the sum of all of the signals being broadcast at once. And how do you compensate for distance or shielding of the signal with?
Yeah, so that's definitely an important issue that we faced, and we have solutions in the paper to solve that. But roughly, for the timing issue, it's very easy to solve because we roughly know the distance using prior regular communication modalities. And we build a Markovian Markov chain model which estimates the channel measurement using past measurements when it was regularly communicating with the client. So these clients regularly operate in normal mode, but suddenly if there's an event like forest fire, we switch to the other mode and operate in that mode only for a small duration. Quail is not a good solution for LP-WANs to operate daily. It's a solution for a quick aggregate information in special scenarios. Yeah.
I have a question.
Yeah.
Which is sort of a practical question. How do you, what are the logistics of getting a CubeSat in space? And can you do it as I guess, an undergrad team, or do you need a lot of money? How many can you put up? Do you have to collaborate with people?
Yeah. So, so the question is very apt, and the thing is that before like SpaceX and all of these relaunch technologies were coming up, the cost of deploying satellite was like insane. No academic lab could actually afford to do that. And in fact, we are truly in an era of democratization of space exploration because of the lowering of the cost of deploying these test beds ourselves. Previously, all of these actual evaluations were kind of gate-kept by big agencies like NASA, ISRO, and the big Chinese and Japanese space agencies, as well as European space agencies. But because the cost of deploying these CubeSats has now lowered, and there are like ride-sharing missions that many of these big companies are doing for universities, we can actually deploy at least a couple or 3 of these CubeSats up in the sky. The cost is not like something you can pay out of pocket as a person, but through research funding, it's pretty reasonable. Like it can, within 500K, you can have a satellite up there. Of course, you need the contacts, you need to build the connections, and as well as we already have an undergrad team which has that connections, like the CubeSat team. So we can kind of leverage those connections to kind of look for opportunities to deploy new satellites. I'll obviously be leveraging my collaborators in my alma mater, as well as I'm in connection with Microsoft Research and many other places to hopefully collaborate with them on the deployment.
Great, thank you. Any other questions? Yeah, Matt.
So you mentioned the idea of leveraging distributed infrastructure that already exists to provide wide area coverage for ground stations. To what extent do those ground stations exist today, and do they have an incentive to participate?
Yeah.
Because obviously they need to maintain these things and whatever.
Yeah, so for example, the most popular IoT distributor in Europe is Things Network, right? They already have LoRaWAN distributions. And the way you can actually monetize this service is like through the application layer protocol. Like, hey, you receive the images, but you'll only get the data if you pay a certain amount of money. And anybody who is deploying a $500,000 satellite up in space can definitely afford to pay a few cents or a few dollars to get that data. And it's a revenue source for both the IoT deployer as well as for the user. And the reason is that now I have a public deployment. I don't need to rely on certain companies to deploy these base stations. I can actually build like systems for the betterment, like just for like public service, like, oh, okay, like we can deploy this using government funds and use public infrastructure to now build services instead of relying on private players in the game. Yeah.
Good, all right. Thank you so much for your talk, and thank you all for attending, and we will see you next week.
Yeah, thank you.
Cheers.